afternoon, everyone. My name is Hwang, and I'm an intern at the SLAC National Accelerator Laboratory, and my project is titled Machine Learning Modeling of Combined Thermal Cycles in RF for Accelerator Injector Systems. So particle accelerators have been used in a myriad of scientific discoveries, right? We saw that with the Higgs boson quark discovery. We saw applications of it in medicine with proton ion therapy. And these accelerators, they're not really simple machines, you know? They have a lot of complex moving parts to it, and it requires a lot of optimization. And one of the parameters that needs to be optimized are something called RF, or radio frequency accelerating cavities, which prepares charged particles, and they use this radio frequency in order to actually accelerate them, right? Because, you know, we're dealing with an accelerator. You gotta accelerate particles, right? You gotta make particles go fast. So this picture right here is the fast gun at Fermilab. So this is actually Fermilab's accelerator. And the reason why I didn't use SLAC's accelerator to showcase my presentation today is because the data I used for machine learning modeling was taken from the fast gun at Fermilab, because their data was a lot more accessible to process and prepare for machine learning modeling. So I'm gonna go into a little bit of how the water cooling system works, right? And how that relates to RF, and why do we care in the first place, right? And we care because it turns out that water cooling has a big impact on the radio frequency that's generated, right? And it's literally dependent on a thermal regulation problem where you're getting a copper cavity in the accelerator literally expanding and contracting due to the heat surrounding the cavity. And that in turn, like I said, affects the radio frequency power. And conventional methods of controlling this radio frequency is through something called, water cooling is something called a proportional integral derivative controller, or a PID controller. So you'll see this right here on this left figure over here, where there's no modeling for this, right? So as soon as you detect, or as soon as the machine detects a change, like this black dashed line is the target line and it's like dipping below it, it's like, oh, I have to take the integral of that and readjust my derivatives and my slopes in order to get back to that solid target temperature and normalize a little bit. So you can tell that compared to something called model predictive controller, which is something that we're using machine learning modeling, it's a lot less time efficient, where you're seeing it takes almost 5 times the amount of time in order to normalize at the target temperature, whereas model predictive controlling takes only about 5 minutes or 4 minutes to really start to get to the target temperature, right? So it turns out that it's a lot more time efficient, and for that reason, we are using machine learning modeling to try to tackle this problem. So here's a little bit of background on how the water cooling system works, right? We have 5 input features for this particular problem. You have the flow valve. So in the water cooling system, there's a literal valve that opens and closes to control how much volume you're letting into the water cooling system, volume of water, that is. And that is measured in percent open. You have the flow rate, so how much actual water is flowing. So it's kind of like the valve and the rate are both controlling the volume here. The flow rate is measured in gallons per minute. And then the water heater power, so the water heater also generates power, which will also affect the water cooling system. That's measured in kilowatts. The gun forward power, which I will note right now, is kept constant at a 6.2 kilowatt measurement throughout the entire experiment. That is also important. And then finally, something called the LCW supply temperature. So that's the temperature of the water coming into the system to begin with, measured in degrees Celsius. And the output that we're looking at is the copper cavity temperature. So remember what I said about the copper cavity literally expanding and contracting. So that is the output, and we want to measure or model our AI so that it reaches a target copper cavity temperature, and that is why we are measuring that as our output. So in my data preparation, I wanted to show you guys a little bit about how data was initially set up, right? So if you look on the top left here, you have the cavity temperature, the flow valve, and the flow rate. And sorry, just a side note, the initial water temperature that is coming into the system was kept at 36 degrees Celsius. I forgot to mention that on the last slide, but I thought that was pretty important. So you'll see here that there are over 14,000 time steps, and every time step represents, in this particular situation, 1 second of time. So if you convert about 14,410 time steps, is exactly how many time steps we had, to number of hours and minutes, you're looking at about 4 hours worth of data from the beam being turned on. And this is just basically sample data of what our inputs looked like, right? So we kind of adjusted the flow valve a little bit, and we also adjusted the flow rate of the water going in so that we can get some data and make the proper optimizations and adjustments to our machine learning modeling, because the big thing about machine learning is that you need to be able to train the AI on multiple scenarios in order for it to be, make more accurate predictions. So I wanted to get into model predictive control a little bit because I brought it up before, and I wanted to introduce it as an alternative to the conventional PID controller that we use. So basically how my machine learning model is going to work is that it's going to look at the past, and then it's going to say, okay, in the past, if these 5 combinations, this combination of the 5 features was probably the best to reach the target temperature. So it basically predicts what's going to happen in the future, right? So basically, you're basically pre-firing what the combination or what combinations of the features or adjustments to the features are the best, which is way more efficient than PID, because think about it, PID, it needs to detect a change in the system in order to act upon it, whereas this is it already knows the future basically, right? So you're saving a lot of time and a lot of energy by doing that. So based on the predictions, yeah, you model the best combination of actions, you execute it, and then you just keep repeating that, right? And for ML, you train the model so that you can know what the future is going to be. So I think this is all really cool, by the way, but we have to choose what kind of neural network that we want to use. And to be honest, this type of research has been done before. However, we haven't really used something called an LSTM structure. So when we try to make a model predictive control in the past, we use something called a feed-forward neural network, where you're looking at a neural network that can also work at predicting in the future, but the problem turns out to be that it doesn't really account for time-dependent behavioral structure, because we are dealing with something called a time-dependent problem, where where it's a dynamic system that'll keep continuously changing as the beam is turned on, right? We're not just seeing like a linear, one faceted way of like adjustments. Like this is a dynamic system, right? As the beam is running, you're seeing adjustments to the features, and you need to continuously optimize as the beam is running, right? So in the past, researchers have used something called feed-forward neural networks, but as you can see here, there's no loops or connections that go back to previous nodes, so it has no past to reference from. It's basically feeding all the information in a forward direction, whereas something I use from this particular project called the long short-term memory neural network, or an LSTM, has that loops and connections to rely off of, and it's a type of recurrent neural network, so you can have a past to refer off of. So as I mentioned before, we got data from Fermilab, the fast gun, and we modeled on 14,410 time steps, which is a pretty good amount of training or data that we had to work with. We, just as a side note, used 2,000 epochs, 0.01 learning rate. Those are just little ML stuff that you can adjust based on you kind of have to test test with that and play around with it, but that's what we use for this particular data preparation. And how the model works is that you're splitting time steps into sets of windows, and you're looking at a certain number of, a certain amount of data at once, and then once you're done learning that data, you're shifting over one time step, then learning the next X amount of data, and then you keep repeating that process until you reach the end. And we used about 80% of our 14,410 time steps to train the model, and then we used 20% of it to test it and see how well it tests or predicts based on our training. And just a side note, we use the atom optimization, which is just a form of stochastic gradient descent, which is an optimization tool that is used for this particular neural network. And so we did the prediction. You can see here this dashed line over here is the training and testing boundary. So that's that 80% mark where we shifted from, all right, let's stop training our model and now let's start testing our model, right? And then you had the blue line, which is the observed data. So that's like what we got the data from Fermilab from. And then the orange line is its own prediction. And it may look like at these peaks it's not predicting as well, but honestly this is not very bad at all, because you have to take into the fact that there's 14,000 data points here. So it turns out that it's a mean squared error of 0.0016, which is pretty good. And basically for our next steps, or just to reiterate what we all did, collectively we successfully trained an LSTM model or neural network to model accelerator thermal cycles. And next time what we want to do is we want to predict 30 time steps ahead. So what my model did was we only looked 1 second ahead into the future and then shifted the window. And then 1 more second ahead into the future and then shifted the window. But we want to predict 30 time steps ahead. So look at 30 seconds into the future instead of 1 at a time, because it takes about 30 seconds for the water to completely cycle through the accelerator water cooling system. So that's why, that's the significance of that 30 time step over there. And we want to put the model into model predictive control and test online, meaning basically we want to run this on simulations. And long term, maybe put it in the accelerator and see and have a much more energy efficient and time efficient accelerator. So I would like to thank everyone for your time. You feel free to ask any questions, and if you're interested, you can visit my website by scanning that QR code. My LinkedIn's also on there, so you can also connect with me on LinkedIn if you want a further discussion. And that's about it. I'll take any questions at this point. Thank you.